things, stress concentrations. Note that the things that it says we're going to learn upon finishing up this chapter is the relationship between lateral strain and axial strain. And we'll talk about Poisson's ratio for that. That's the first thing we do. How that ratio is related to the modulus of elasticity and rigidity. How to determine the expansion and contraction of engineering materials caused by temperature variation. I kind of find that kind of neat. You know, what's the temperature going to do? You do have to rely on that, don't you? You have to account for that. So we'll do that. That's a couple of problems there that we'll probably get to yet today. Let's see what else. How to calculate the stresses induced in structural members by that expansion and contraction, or contraction. Let's see, we gotta click that button. And let's see what else here. How to determine the effects of expansion and contraction on non-homogeneous members, in other words, things that are different makeup, and how to calculate the normal and shear stress in an object on planes inclined to the cross section. So a lot going on there. So again, it'll take us probably a week at least to get through that. So Poisson's ratio. So what's the deal there? It says the concept is you've got a body of elastic material and it's subjected to tensile or compressive stresses. Okay, and let's see, do they have I don't remember if we've got a picture for that or not. Yeah, this one right here actually. So it's subjected to axial or tensile or compressive stresses. And what's happening there then is the concept is that the transverse dimension, that's, if you will, if this were like a bar, a piece of round stock, the transverse dimension would be the diameter, right? The transverse dimension decreases at the same rate basically as the same time as the axial dimension in the direction of the load. Okay? So in other words, as that thing stretches, it's also going to neck down. It's what you see in that I'm drawing blank now, the Tennis Olson machine downstairs. Thank you. That's basically what they're saying. There's a proportion there that can be talked about. Okay, and there are some other things that will go along with that we'll see some data that's already been determined on a lot of that stuff. So it'll stretch and neck down if it's a tensile load. If it's compressive, then it's going to do just the opposite. Okay, it'll get shorter and the diameter will get bigger. You know, it's going to bulge out, isn't it? So that's what, and that Poisson's ratio will address that. Okay. Let's see, what else on that? Now they do have a problem there, and note that Poisson's ratio is signified by that mu. So there's, let's see if I can find my cursor now. Oh, I can't find it because I don't have it turned on. Does make a difference. Come on. So again, that's mu equals the transverse strain, right, divided by the axial strain. So that's that relationship and that ratio. That's where you get the ratio. It's you have to divide one by the other, right? Okay. Let's see. So anything else on that? Note it does say, and that's the equation 11.1. Commonly used values for Poisson's ratio are given in Appendix G. So that's pointing you in a direction, right? So when we have problems, you might need to go back there and check it. So that's what's going on there. Now they've got example 11.1, and it looks like we don't have any pictures or anything for that one, so we don't have to go there looking. But what are they saying then?